Okay, let's be real. In just the last few years, AI has gone from kind of a neat but clunky tech to something else. It's creating incredible art, writing poetry, even coding software. It feels like we jumped forward a decade overnight. But what if I told you that this entire explosion, this whole revolution, was basically sparked by a single research paper from 2017?
I mean, that's the big question, right? Why did AI suddenly get so powerful? How did we go from those old, frustrating chatbots to something like ChatGPT that you can actually talk to? You might think, oh, it's just bigger computers and more data. And yeah, that's part of it, but it's not the real story. The real secret sauce was a complete shift in how these AI models actually think. And the answer? It's right here. A 2017 paper from a handful of Google researchers. The title sounds almost poetic, right? Attention is all you need. But don't let the simple name fool you. The idea inside was so potent, so game-changing, that it literally became the blueprint for pretty much all the AI you're hearing about today. So let's unpack this thing. Let's figure out what made this one paper so incredibly important.
All right, here's our game plan. We're going to start with the big problem they were facing back then. Then we'll get into their totally radical idea for solving it. We'll peek under the hood to see how this thing called the transformer actually works, look at the insane records it shattered, and then we'll connect all the dots to the AI revolution that's happening right now. And finally, we'll talk about its legacy.
Okay, first we need to rewind a bit. Before 2017, if you were working with language AI, you were almost certainly using something called a recurrent neural network, or an RNN. This was the gold standard, but it had a massive fundamental flaw that was holding everything back. You see, these older models processed language sequentially. The paper calls it an inherently sequential nature, which is a fancy way of saying they had to read one word at a time. Think about it like trying to read a whole book through a tiny keyhole. By the time you get to the end of a long sentence, you're struggling to remember how it even started. That's exactly the problem these AIs had. And this one word at a time thing created a huge bottleneck. For one, it was super inefficient. You couldn't just throw a bunch of processors at the problem to speed it up because you had to go in order. And second, these models were, well, they were forgetful. By the end of a long paragraph, the AI would basically have no memory of what was said at the beginning. This made understanding the full context, connecting ideas across a text, almost impossible. Okay, this table right here, this is the whole ballgame. It's a simplified version from the paper, and it shows the core problem and the brilliant solution. With the old way, the recurrent models, look at that O of n. That just means the number of steps it takes to connect two words depends on how far apart they are. So in a 50-word sentence, it takes 50 steps to connect the first and last word. It's slow. Now look at the new way, self-attention. It's O of 1. Constant time. That means it takes exactly one step. 1. It doesn't matter if the sentence is 10 words or 10,000 words long. It can connect any two words instantly. This wasn't just an improvement. It was a fundamental breakthrough in efficiency. So this brings us to the team's absolutely radical idea. They looked at this one word at a time bottleneck that had defined the entire field, and they just asked, hey, what if we just stopped doing that? What if we threw the whole thing out? And this quote from the paper's abstract basically sent a shockwave through the AI world. We propose a new, simple network architecture, dispensing with recurrence and convolutions entirely. I mean, think about that. They were telling everyone to throw away the main tools they'd been using for years. They were going to build something new from the ground up based on just one single idea: attention. And that right there is the core shift. We're getting rid of the keyhole. Instead, the transformer architecture just throws the doors wide open. It lets the model see the entire sentence all at once in a single snapshot. This means it can instantly see how every word relates to every other word, no matter where they are. The context is global, and it's immediate. So, okay, this sounds like magic, right? Seeing the whole sentence at once? How does that even work? Well, the engine driving this whole thing is a mechanism called self-attention. And yeah, it sounds a little technical, but the basic idea is actually something we can all wrap our heads around. Basically, here's what it does. For every single word in a sentence, the model asks itself a question. To really understand this word, which other words in this sentence are the most important? It's not just looking at the words next to it, it's looking at all of them and deciding which ones have the strongest connection, which ones add the most meaning. It's building a map of relationships for the entire sentence.
A really great way to think about it is like a super smart internal search engine. The word it's focusing on sends out a query. That's it asking, who's relevant to me? All the other words in the sentence hold up their keys, which are like little signs saying, here's what I am, here's my identity. The query then matches itself with the most relevant keys and pulls in the values or the meaning from those words. And it does this whole dance for every single word all at the same time.
But they didn't stop there. They thought, why have just one of these smart searches running? Why not have a bunch of them running at the same time? This is called multi-head attention. And you can picture it like a committee of experts all reading the sentence together. One head or expert might be looking at grammar. Another might be figuring out who it refers to. A third might be tracking the main theme of the sentence. The original paper used 8 of these heads, all working in parallel, each learning a different kind of relationship. It's not just reading, it's analyzing from multiple perspectives at once. So you've got this wild new idea, this crazy new architecture. But the big question is always the same. Does it actually work? Is it any better? The researchers had to prove it, and they put their new transformer model up against the toughest challenge in the field. Back then, the ultimate test for any language AI was machine translation. It was like the Olympics, and the specific event was the WMT 2014 dataset. This was the gold standard benchmark. If you could get a high school here, you had everyone's attention. And the results? Well, they weren't just good, they were incredible. This chart shows the quality score they used, called a blue score. Higher is better. On the left, you see the scores of the previous best models, and then look at the transformer on the right, 28.4. It didn't just beat the record, it completely shattered it. Now, a jump of 2 points might not sound like much, but in this world, it was absolutely massive. People would fight tooth and nail for an improvement of like 0.1. A 2-point jump was basically unheard of. They didn't just move the goalposts, they put the stadium in a whole new city. They set a new state of the art, literally overnight. And here's the kicker. This is what really sealed the deal. It wasn't just better. It was way, way faster and cheaper to train. Because of the parallel design we talked about, you could just throw a ton of computer hardware at it and it would train incredibly fast. The paper mentions training their big model in just 3.5 days on only 8 GPUs. That was a fraction of what it took for the older, less accurate models. So now you have something that's both higher quality and more efficient. That combo is unbeatable. So that amazing performance did more than just win a competition. It handed the entire AI community a new blueprint, a new recipe. And that recipe is what kicked off the generative AI explosion that we are all experiencing right now. I mean, just look at this. Every single one of these things that are changing the world, they are all direct descendants of that 2017 paper. The T in GPT from ChatGPT, it literally stands for transformer. Google's Gemini, Meta's Llama, all the AI art and video generators, they are all built on this fundamental architecture. It turned out this idea wasn't just good for translating languages. It was a revolutionary way to understand patterns in almost any kind of data. So, as we bring this all home, what's the big takeaway here? What's the lasting legacy of attention is all you need? What's the one thing that really, truly changed the game? Well, the key mechanism was called attention, but the real magic, the true breakthrough, was parallelization. By destroying that one word at a time bottleneck, transformers made it possible to build models that were bigger and bigger and bigger. You could finally train them efficiently on the unimaginable amount of data on the internet. It unlocked the ability to scale up. And as we've learned, in the world of modern AI, scale is pretty much everything. So the transformer brilliantly solved the sequence problem and laid the foundation for the entire era of AI we're in now. But it also makes you wonder, right? It leaves us with this huge, exciting question. What's the next bottleneck? What's the next big problem that if someone solves it, will kick off the next AI revolution?